Hello everyone. Here we are going to learn about some of the fundamental identities in trigonometry. Now there are a whole set of identities in trigonometry and we will learn about them as we go along in this course. However, today we'll start with the reciprocal identities, the quotient identities, and a few slides later we will also talk about the Pythagorean identities. Knowing identities is very important because they help us easily find trigonometric values of different functions. It helps us solve complex trigonometric equations or simplify complicated trigonometric expressions. So starting off with the reciprocal identities, we've already touched upon them previously when we learnt about the six functions, and we said that the sine function and the cosecant functions are reciprocals of each other. The cosine and the secant are reciprocals of each other, and tangent and cotangents are reciprocals of each other. How do we find the reciprocal of any value? We can find the reciprocal by performing this operation: 1 divided by whatever value you want to find the reciprocal of. So if the value or variable is x, then its reciprocal is 1 divided by x. If the number that you want to find the reciprocal of is 5, the reciprocal is 1 upon 5. So 1 divided by any value gives the reciprocal of a number. If it's a fraction, for example 2 over 5, then the reciprocal of that is 1 divided by 2 over 5, and you will end up flipping the numerator and the denominator of this fraction, which will give us 5 divided by 2. So essentially, when you find the reciprocal, of course you're doing 1 divided by a particular value, whether it's fraction or an integer, but essentially what you end up doing is flipping the numerator and the denominator values of the number. So again, sine of t is 1 divided by cosecant of t. Cosecant of t is 1 divided by sine of t, and it's the same for the cosine, which is 1 divided by its reciprocal, which is secant of t. Then secant of t is 1 over cos of t, tan of t is 1 over cot, and cot is 1 over tan. So these are the reciprocal identities, and it's relatively easier to remember these identities. The quotient identities is the next set of identity where we have tan of t is sine of t divided by cos of t. So if you are given the sine function or the value of a sine as well as the value of cosine, you can find the tangent value by taking the sine and dividing it by the cos. As far as the cotangent function is concerned, it's the reciprocal of tan, so it's going to be cosine over sine. I'm going to quickly prove how this identity is true. So recall that tan is defined as opposite over adjacent, right? Opposite side over adjacent is the definition of the tangent function. The sine function is defined as opposite over hypotenuse, whereas the cosine function is adjacent over hypotenuse. Now, when we do this division of this fraction, how do we go about that? We keep the numerator fraction as is, opposite over hypotenuse. We change the division into multiplication, and then we flip the numerator and denominator of this entire fraction in the denominator. So this becomes hypotenuse over adjacent, and hypotenuse divides. So we are left with opposite over adjacent, which is exactly what we have as the definition of the tangent function. So we can remember this easily as well. Tan equals sine over cos, and cotangent equals cos over sine, and you can prove this using the same process that I worked to prove the tangent quotient identity. We are now going to work through an example where we will need to use the quotient and the reciprocal identities. I'm going to read through the question. It says, given sine of t equals 2/3 and cos of t equals square root over 5 divided by 3, find the value of each of the 4 remaining trigonometric functions. So we've just been given the value of the sine function and the value of the cosine function. Given just 2 of these function values, we should be able to find the remaining 4 trigonometric functions. For the tangent function, we will need to use the quotient identity. For the rest of the 3 functions, we are going to use the reciprocal identities. All right, so let me work through it first and then we'll pull up the solution. Sine of t has been given to us as being 2/3 divided by cos of t is square root over 5 by 3. So let's write square root over 5 by 3. And now we have to perform the division. We write 2/3 multiplied by, we change this division to multiplication and we flip the values in the denominator. So it's going to be 3 divided by square root over 5. 3 and 3 cancel out. It divides and we are left with 2 divided by square root over 5 because we have a radical sign in the denominator. Let's rationalize it. We multiply the numerator and the denominator both by square root over 5. So we end up with 2 times square root over 5 divided by 5 should be our answer for tan of t. All right, so I'm going to now erase this and see if the solutions they've given us is the same as 2 times square root over 5 divided by 5. So here they have done the same thing that we had done. They took the sine function value 2/3, divided it by the cosine function value square root over 5 divided by 3. When they performed the division the same way that we had done, they flipped the denominator fraction, wrote it as 3 divided by square root over 5, and they multiplied the two values here, and then they came up with 2 divided by square root over 5, and then they rationalize the denominator by multiplying both numerator and denominator by square root over 5 to get a final answer of 2 times square root over 5 divided by 5 as the value of the tangent function. The next is to find the reciprocals. Cosecant of t is 1 divided by sine of t. So essentially they should get 3 over 2, right? Reciprocal of sine would be 3 over 2. Reciprocal means 1 divided by the value. So 1 divided by 2 over 3, which is 3 over 2 for the cosecant of t. So we still need to find the secant function and the cotangent function, which we complete in the next slide. Now here we are going to find the remaining 2 functions, the secant and the cotangent functions. So I'm going to pull up the solutions here. We know secant is equal to 1 divided by cos of t. So just plug in the value square root over 5 divided by 3 into this equation, into this identity, and then evaluate it to come up with the value of secant t. So let's pull up the results. Here we have 1 divided by square root over 5 over 3. And now we have to simplify this. That gives us 3 divided by square root over 5. Because we have a radical sign in the denominator, we need to rationalize this by multiplying both the denominator and the numerator by square root over 5, and that's exactly what they did here. They multiplied both the numerator and the denominator by square root over 5 and came up with a value of 3 times square root over 5 divided by 5 as the answer for secant of t. The next one is cot of t, which is 1 divided by tan of t by the reciprocal identity. So you have to plug in the value of tan that we found using the quotient identity. So that value was 2 times square root over 5 divided by 5. So that goes in the denominator under 1. And when we simplify this, we get 5 divided by 2 times square root over 5. and then we again have to rationalize this, and we eventually come up with a value of square root over 5 divided by 2. We are now going to learn about another set of identities called the Pythagorean identities. There are three trigonometric identities under the Pythagorean family of identities. They are all derived from the Pythagorean theorem. But let me just read out these three identities first. The first one says sine squared t plus cos squared t equals 1. Then we have 1 plus tan squared t equals secant squared t. And then 1 plus cot squared t equals cosecant squared t. I'm going to also put up the Pythagorean theorem here, which says a squared plus b squared equals c squared. And I'm going to draw here the figure of a right triangle because Pythagorean theorem is based on a right triangle. Here we have our right triangle, the right angle labeled as c. The side opposite to it is denoted by the lowercase c. Then we have the two acute angles A and B, and let me label the sides opposite to them with the lowercase letters of each of the corresponding angles. So we have A, B, C. And what the Pythagorean theorem a squared plus b squared equals c squared essentially tells us that in any right angle triangle, the square of the side A plus the square of the side B will always be equal to the square of the hypotenuse, which is c. So a squared plus b squared equals c squared. Now I'm going to use this theorem to prove that sine squared t plus cos squared t equals 1. So I'm going to take an angle here. Let's take angle A, and recall that the sine function of angle A would be opposite over hypotenuse. Therefore, in this case, in this picture, that would be A over C, correct? Considering that we are looking at this angle A. So it's going to be A over C. The cosine of angle A is going to be adjacent over C. So B over C. So I'm going to write here adjacent over hypotenuse, which is B over C. And now I'm going to add these two ratios and see if we come up with an answer of 1. That's going to prove that sine squared t plus cos squared t equals 1. So I'm going to write here A over C whole squared plus B over C whole squared. I'm going to add them up. So I'm going to get A squared over C squared plus B squared over C squared gives us A squared plus B squared divided by C squared. And by the Pythagorean theorem, A squared plus B squared is equal to C squared. So I can replace the numerator expression A squared plus B squared with C squared, and I will end up with C squared divided by C squared, which is equal to 1, correct? So that proves that sine squared of t plus cos squared of t is equal to 1. So we've just proved the first Pythagorean identity in trigonometry. In the same way, you can also show that 1 plus tan squared t equals secant squared t. Now, secant is the reciprocal of cosine. When we add 1 to the square of the tan function, we should end up with the reciprocal of the cosine function squared, correct? So tan of A is opposite over adjacent. So based on this picture of this triangle here, it's A divided by B. So let's add 1 to the square of A over B and see if we are getting secant square of A. Alright, so 1 plus A divided by B whole square, which is the tangent definition, is it equal to the secant square function? So 1 plus A squared divided by B squared is going to be equal to B squared plus A squared divided by B squared. So what is b squared plus a squared, the numerator? B squared plus a squared is as good as a squared plus b squared. So it's equal to c squared divided by b squared, which is c over b whole squared, and that is the reciprocal of the cosine function squared. Correct? Cosine was b over c. Its reciprocal is c over b squared, and we've just proven that 1 plus tan squared t is equal to secant squared t. And in the same fashion, and I will leave that for you to prove it, but use the same process that I just showed here to prove that 1 plus cot squared t is equal to cosecant squared t. So what you'll be essentially doing is 1 plus b over a whole squared, and see if you end up getting 1 over sine squared. Cosecant squared is the reciprocal of sine squared. All right. Here we have an example where we will be applying one of the Pythagorean identities to solve the given problem. Let's read through the problem. It says, given that sine of t equals 1/2 and t is an angle between 0 and pi over 2, find the value of cos t using a trigonometric identity. Now we learnt about 3 Pythagorean identities. However, we have to choose the identity which had both sine and cosine in its equation, because here we've been asked to solve for cosine. So let's first solve it ourselves, and then I will pull up the solutions to see if that matches with the way we are doing it. All right, let's write down the identity that had both sine and cosine in it, and that was sine squared t plus cosine squared t is equal to 1. Correct? So we have on the right hand side a constant value 1. We know what the value of sine of t is, 1/2, and we are going to plug that into this equation. Cos of t is what we need to find, but once we plug in the value of sine of t, we should be able to solve for cos of t. So let's do that. Sine of t is 1/2, but we have to square that, so I'm going to write it as 1/2 squared plus cos squared t equals 1. Half squared is 1 over 4 plus cos squared t equals 1. Now in the next step, we have to isolate cos squared t on the left hand side and bring over the 1/4 on the other side. We are left with cos squared t on the left hand side, and we bring over 1/4 on the other side, so it becomes 1 minus 1 over 4. And now we have to do the subtraction, so we do cos squared t equals 1 minus 1/4 is 3 over 4. Next, we take the square root of both sides, and we have cos of t equals square root over 3 divided by 2. So that should be our final answer. Let's pull up the solutions now, step by step. So they have chosen the same Pythagorean identity that we had. Sine squared t plus cos squared t equals 1. In the next step, they plug in 1/2 into sine of t and square it. So we have half squared plus cos squared t equals 1, which is again the same that we did. And then 1/4 plus cos squared t equals 1. They move the 1/4 over to the right hand side to isolate cos squared t. Now we are solving for cos of t, correct? And then we have cos squared t equals 3/4. In the next step, they should take the square root of both sides and come up with cos of t equals square root over 3 divided by 2. All right? We are now going to be introduced to an important concept in the study of trigonometric functions, and that is of a periodic function. Now, all the 6 trigonometric functions are periodic functions, but what do we understand by a function being periodic? In simple terms, it is when the function values repeat themselves after regular intervals. In other words, they occur in a cyclical fashion. Now, I'm going to explain this using the example of the sine function. But before that, let's read through the description of a periodic function algebraically. It says here a function f is periodic if there exists a positive number p such that f of t plus p equals f of t for all t in the domain of f. The smallest positive number p for which f is periodic is called the period of f. In other words, the period of a function represents the interval of time after which you will see the function values repeating themselves. So what's going to happen is after completing one cycle represented by the value of p, you will see that the function values are staying the same, but the input values are changing because you are adding p to your initial domain value, the initial input value. So at this point, let me pull up a circle and I'm going to use the sine function to explain a little more on what this periodic function implies. So here we have a circle and we know that the 0 radian angle is on the positive x-axis. So when the initial and the terminal side overlap, we form what's called a 0 radian angle. And as the terminal side moves around, whether in the anti-clockwise direction or in the clockwise direction, it forms different angles with the initial side, correct? So as the terminal side moves, we can have a pi over 4 radian angle, we can have a pi over 2 radian angle, we can have a 3 pi over 4 radian angle, then we can have pi radians, 3 pi over 2 radians, and then once the terminal side completes a full cycle and comes back to the initial position, it will have formed 2 pi radian angle, and it can keep moving around and around, forming many different angles of different radians. But what happens is once it comes back to the initial position, the function values will start repeating themselves. So even though the angle values will change after every 2 pi period, the function values will remain the same. For example, sine of 0 and sine of 2 pi will have the same function value of 0. Likewise, sine of pi over 4 and sine of 9 pi over 4 is the angle that you get after completing 2 pi rotation. 2 pi over 4 will give us a function value of square root over 2 by 2. So I'm going to use this pi over 4 radian angle and represent it algebraically. Initially, we have sine of pi over 4. The initial domain value of t was pi over 4, and that had a function value of square root over 2 by 2. However, after completing 2 pi rotation, we will have sine of pi over 4 plus 2 pi, because the period of the sine function p is 2 pi, t was pi over 4, we will have sine of 9 pi over 4 as our input angle, but the function value of sine of 9 pi over 4 will still be the same as sine of pi over 4, which is square root over 2 by 2. So that is what we mean by a function being periodic. Now in subsequent slides, we will talk a little more about the sine, cosine, the cosecant and the secant functions. We will see that all 4 of those functions have the same period of 2 pi, whereas the tangent and cotangent, even though they are periodic functions, they have a different period. All right? Now here we will talk about the periodic properties of the sine and the cosine functions. Previously, in the example of the sine function, we saw that the function values for sine repeat themselves after cycles of 2 pi. So in that case, the sine function has a period of 2 pi. The cosine function also has the same period as the sine function, which is 2 pi, and that's the case also for the reciprocal functions of cosecant as well as secant. Now, as far as the tangent and the cotangent functions are concerned, they are also periodic functions, but their periods are different from that of the sine and the cosine. The tangent and the cotangent have a period of pi units. That means their function values will repeat after every pi cycles. We'll now go through an exercise of applying the periodic properties that we just learned to find different trigonometric function values. The first example is cot of 5 pi over 4. The way to go about it is first break up 5 pi over 4 and rewrite it as a first quadrant angle plus pi units. Recall that both the tangent and the cotangent functions have a period of pi units, which means that the ratios are going to repeat themselves after every pi cycles. So if we can break up 5 pi over 4 and write it as a special angle in the first quadrant plus pi units, then it'll be easy for us to find the ratios. So cot of 5 pi over 4 can be rewritten as cot of pi over 4 plus pi, which means that whatever the cotangent ratio is at pi over 4, it'll be the same for cotangent of 5 pi over 4. Therefore, cot of 5 pi over 4 equals cot of pi over 4, which is equal to 1. So that is how we have applied our knowledge of periodic properties to find the cotangent of 5 pi over 4. The next one is cos of negative pi over 4. Now here we will apply two pieces of information. One is that the cosine is an even function. Therefore, whatever the ratio of cos of negative pi over 4 is, it'll be the same for cos of positive 9 pi over 4 and vice versa. So first we will have to apply our knowledge of the even odd properties of trigonometric functions, and we'll write it as cos of negative 9 pi over 4 is the same as cos of 9 pi over 4, and then we'll try to break up 9 pi over 4 and write it in terms of 2 pi and a special angle. You have to remember that the period of the cosine as well as the sine function is 2 pi. It's not pi. Pi is only for tangent and cotangent. For cosine and sine, it's 2 pi. Therefore, we rewrite 9 pi over 4 as a special angle in the first quadrant plus 2 pi, the period of the cosine function. And therefore, cos of pi over 4 is equal to square root over 2 by 2, and that is going to be the same as the cos of 9 pi over 4 and cos of negative 9 pi over 4 using the periodic property. Let's summarize the repetitive behavior of the sine, cosine, and the tangent functions now. We have sine of t plus 2 pi times n equals sine of t. So it's not just one period added to t, but it's multiple periods. That means you can keep going around 2 pi multiple times and add it to t, and you'll get the same ratio as sine of t. Same for cos of t. So cos of t plus 2 pi times n. N representing the number of times you're making 2 pi circles. All right, it'll be equal to cos of t, and finally tan of t plus pi over n equals tan of t. So because the period for the tangent function is pi, it's going to be n times pi plus t. It'll give you the same ratio as tan of t. So that's the way to represent the repetitive behavior of the sine, cosine, and tangent function in notation form.